Welcome, ladies and gentlemen, to this afternoon's lockdown lecture. It's a little bit later in the day because our guest speaker is based in Seattle in the United States. So it's a bit early for him and a bit late in the day for us. But Dillon Amaya, and I hope I've pronounced that correctly, is a climate scientist working as a postdoc at the University of Colorado in Boulder, although he's staying in Seattle. He got his BSc in meteorology at the Texas A&M University and his MSc and PhD in oceanography at Scripps Institution of Oceanography in San Diego. So he's been around the block to some pretty well-respected institutions. His research is aimed at understanding internal and forced climate variability and change using observations and model simulations. Nolene tells me she'll put more information into the chat while Dillon is speaking, and I think there's going to be a couple polls coming up. Dillon, with that, if you can take it away, welcome everybody. I think it's going to be an enjoyable talk.
Awesome. Thank you guys so much. I really appreciate the invitation to speak with you, and thanks for those that were able to make it. I understand it's later in the day for you. As Craig mentioned, it's early for me, so I appreciate you hanging around at the end of your workday like this. But as Craig said, I'm a postdoc at the University of Colorado Boulder. Actually, starting to transition to a new position. I'm going to start working for the federal government in the United States for NOAA as a research scientist here this upcoming fall, I guess. But so today I'd like to talk to you about this concept of climate change and the way we perceive climate change as a whole, both as individuals and as societies, and how we make the decisions based on that perception of climate change, and whether we perceive it as a risk and how it leads to an overall sense of urgency, individually, for how we prioritize it, when we make decisions about what we vote for, or what kind of industry, or what kind of environmental causes we want to put our money behind and our time and effort behind. But before I get started, I'd like to get a better sense for who I'm talking to. Craig gave me a little bit of a rundown about what GSSA is about, but I would really love to know a little bit more about those that are actually physically here now, and maybe a little bit more about your expertise. Can you just maybe type in the chat? Just give me like one or two words that sort of describe what you do, maybe your background, if you have a PhD, and what, that sort of thing. Craig mentioned that most people in GSSA are industry, but I would still be interested to know generally what everybody's doing, so I have a better sense of what level to push for. So maybe just a couple words in the chat would be really appreciated, if you can find it. And for those that may not know, the chat should be at the bottom of the screen. There's a little bar that will pop up, and just click, I guess, just chat, and that should pop up. Maybe. Or you can just shout it out. I mean, there's so few of us, I'm happy to just have a round table discussion. Independent consultant, okay. Long time in industry. Yeah, and if you do work for industry, I'd be interested to know, what kind of industry are you in, like the energy sector, or I guess I'm not super familiar with the industrial side. Dark side, service provider. Okay. Great. Okay. Well, yeah, so it sounds like we're a relatively diverse group. Like I said, my background is primarily academic. So my perspectives are, they're going to be skewed more towards the academia, but I'm happy to hear, questions and comments from those from other areas, like, there we go, like consulting environmental geologists. So I would prefer this to be more of a discussion. So please, if anybody has any questions as I go through all of this, please feel free to interrupt me and ask your question. We can also save some questions for the end. But yeah, I'm happy to have more of a discussion and less of me just talking at you for a little while. But with that, I'm going to get started here. Today, like I said, I really want to talk to you about this concept of climate change. And what people tend to think of when they think of climate change is this idea of global warming. And that's basically what I'm showing you here. This is a map of surface temperature changes that we've observed since about 1860 at different places all over the globe. And you can see that some places are warming much faster than others, like the high Siberian plains in Russia, and also in Canada. Different parts of Africa and South America are warming much faster than other parts of the globe. But what's interesting, both in academia and in the media, we tend to report, we never almost never show this map, particularly in the media. And I kind of wish they would, because then people would get a better sense of what's actually going on. But really in the media, to simplify things, we tend to boil this down to a globally averaged value, to make it more, I think people think that it's a more attainable number for the average person to quite understand, but I actually think it obscures a lot of things. So right now, since 1860, we've experienced about a degree Celsius of global averaged surface temperature change, about a degree Celsius change of global warming. And this global value is really, it's helpful in the sense that it boils down a lot of complicated factors into some one number. But as I said, I think it obscures a lot of the intricacies of the problem. And it makes it really difficult for an individual person in an individual place to assess, like the actual risk of climate change and be able to understand what is happening to them. Because, we don't step outside and experience global warming, right? If I step outside here in Seattle, and it's like a really hot day, I don't say, oh, global warming is really, really bad today, right? I say, oh, it's just a sunny, warm day. I don't have any baseline to compare global warming to. When in reality, when you step outside, you're experiencing the impact that global warming and climate change has on, the day-to-day weather events that you experience, right? And that can lead to, drastic changes in things like extremes. In the United States, for example, I'm sure this is true of many places around the world, but some things that we focus on in particular are, the impact of climate change on things like wildfires, particularly along the United States West Coast, tropical storms, tropical cyclones, hurricanes that make landfall. We have very good evidence to suggest that climate change is going to influence, the intensity and duration of landfalling hurricanes, and also drought, right? The United States West Coast is very sensitive to small changes in the availability of water. And we think that climate change is influencing all of these things. And so when you take a global average value like this, you really minimize, in a way, the impact that climate change is having on an individual, because you're not giving the regional information that is important for an individual person. You're sort of just lumping it all together in this aggregate sense, and that's not particularly helpful, I think. But the media has tried, right? Newspapers and news outlets have tried to sort of communicate the impacts of climate change on individuals through the lens of these extreme events. And so here are three examples of that here. These are three newspaper headlines from three newspapers in the United States. And you'll have to forgive me. A lot of this presentation is going to be, relatively United States focused, just because that's where I'm based. But I think a lot of these problems pertain to other parts of the world as well. But here are three headlines one's from the LA Times. It says, thanks to climate change, hurricanes pummeled land longer. New York Times, Southwest droughts, and they're referring to the Southwest United States here. Southwest droughts rivals those of centuries ago thanks to climate change. And then I got my PhD in San Diego. So this is a San Diego newspaper, and it said climate change helped produce San Diego's huge ocean heat wave in 2018. So these are the media's attempts, or the scientists' attempts through the media, to communicate the risks of climate change through these individual sort of high impact events, so that, people that are reading these things can get a better sense for how climate change is influencing them, right? And sort of moving the conversation away from global warming to risk assessment associated with these extremes. That's really the kind of perception I want to build for everybody today, is get a better appreciation for how climate change is impacting, individuals throughout the globe, not just in South Africa, not just in the United States, but, everywhere. So to get started, I want to do a series of polls or series of questions, and these are some questions that were actually posed by Yale University to adults all over the United States. And they asked them these same sorts of questions to get a better sense for how people understand climate change and how people understand global warming, and how they understand the risk that these global warming and climate change pose them individually. So basically what I'm going to do is I'm going to ask you those questions. And I think Nolene has, yes or no polls that are going to pop up on your screen. All you do is you click yes or no. If you, yes, meaning you agree with the question, or no, meaning you disagree with the question. So Nolene, let's set up that first question, that first poll. And the question is, so just click yes or no, do you think global warming is happening? And it's a totally anonymous. So, feel free to say what you like. But yeah, do you believe global warming is happening? This will populate as people are answering the question. and we'll just do a couple seconds. Okay. Looks like we're missing a couple votes, but maybe one of those might be actually me. Okay. All right. Great. So we have a handful of yeses, a couple no's, and that's okay. Hopefully by the end of this presentation, you'll have a better appreciation for what's going on or what we think is going on. Well, so I'm going to show you the results now in the United States. Here's Yale University asking that that question of adults throughout the United States, and here's the aggregated result. I got a lot of little windows on my screen. Got to get them off the screen. There we go. And this is broken down by state within the United States. So each of these are these individual little provinces or states that the United States has. And here's sort of the average value. Sorry, I'm getting a lot of pop-up windows for people trying to be admitted. Here's the average value that for each of those states. And so the national average in the United States says that about 72% of adults who answered this poll agree that global warming is happening. And you can see sort of the regional variation in the way people think. For reference, I'm assuming you can see my cursor. Maybe Nolene or Craig can confirm with me real quick. Can you see my cursor?
We can see it.
Okay, great. So I'm way up here in Seattle right now. I should be working over here near Denver, but because of COVID, I'm working remotely in Seattle. I grew up in Kansas City, Missouri, which is here. I went to undergraduate. My undergraduate was down here in Texas, just north of Houston. And then I got my PhD down here in San Diego. So like Craig said, I've sort of been around the block in the United States. But anyway, all of that is to say, most of the United States adults believe that global warming is happening. And of course, these sorts of polls have, a lot of stuff goes into these. The kinds of people that answer these kinds of polls are obviously going to be a certain subset of the population. They obviously try to spread out, try to get a reasonable sample of the population, not just, academics or people who have, had some sort of formal education, but yeah, this is just an example of how parts of the United States are thinking. Okay, so another question that we can ask here is, and maybe we'll set up the second poll, Nolene, is, assuming that we think global warming is happening, do you think that global warming is mostly caused by human activities? Yes or no? Or do you agree or disagree with the statement that global warming is caused by human activities? Okay, and this is populating. I guess you all probably can't see the poll results, but I can. They're populating now. It looks like we have, mostly yeses, a couple no's, and that's okay. Again, hopefully by the end of this presentation, we can begin to have a conversation with some of those no's about why or why not they think that way. Okay, so that came through, like I said, mostly yeses. And this is the results in the United States for that same question. This is the estimated percent of adults who believe global warming is mostly caused by human activities. And right away, you're going to see that this map got colder, right? The national average has dropped to 57%. And you can see sort of this degradation, right? The breakdown in the communication between, the scientists, people like me, through the media to the general population about, the complex idea that global warming is driven by human activities. And you can see that this doubt that's starting to get sowed into people's minds about, what is global warming actually representing? Okay, so another question that we can ask ourselves here is, do you think scientists think that global warming is happening? So not just do you think global warming is happening? Do you think scientists, climate scientists like me, do you think they think that global warming is happening? Okay, and this is populating. We're getting a very similar distribution, mostly yeses, a couple no's. And I understand that we obviously have a very small sample size relative to this overall poll, but it's just interesting to see. Okay, so yeah, again, mostly yeses, a couple no's. This map always boggles my mind, but this is the result in the United States, right? This is the estimated percentage of adults who believe that most scientists think that global warming is happening. And this, like I said, it boggles my mind. Most of the adults in the United States think that global warming is happening, but also most of the adults in the United States don't think that scientists think that global warming is happening. And that right here represents, I mean, this is the issue, right? This is the breakdown in communication between climate scientists such as myself and the general population, and also sort of this war between politicians and scientists to, it just leads to disinformation and overall distrust in science, at least within the United States. And again, like I said, this is mostly United States focused. And in the United States, we have a serious problem where people just don't trust science. And they don't believe that scientists, a lot of people believe that scientists have an agenda, right? And they're trying to just drum up funding, and they're making a problem out of nothing just so that they can get paid. I'm here to tell you that's not how it works, but this is sort of a representation of that issue, right? Okay, so final question for you here. And this one's more about risk assessment. Assuming you think or don't think that global warming is happening, do you agree with the statement that global warming is already harming people in your local community? So either in the United States or South Africa or wherever you are, do you think that global warming is already harming you today? Okay, and so this one, this is an interesting poll here because now we have maybe the most symmetric distribution that we've had so far. We have about half yeses and about half nos, whereas before we had mostly yeses and a couple nos. Now we have about half and half. So that's really interesting to me, and that's going to be what a large portion of this presentation is about. Is to what degree is climate change perceptible to you today, or should it be perceptible to you today? Okay, so that's our last poll. But I'll give you a look at, what does the United States think about this? They asked the same question, and this is the estimated percentage of adults who think global warming is already harming people in the United States today. And you can see that there is a really interesting spatial distribution in the perceptibility or the perception of climate change, as an individual risk assessment across the United States, across this country. And for anybody that knows anything about the distribution of, socioeconomic and political will in the United States, you'll know that this is roughly divided somewhat on political lines, but also there's some really interesting geographical features here, right? There's in the northern part of the United States, there's these really like great plains. It's mountainous, but there are also lots of farming going on. And in the western United States, it's really dry, really water stretched. And this is also where a lot of agriculture goes on. The Southeast United States is typically a pretty Republican part of really conservative part of the country. Like I said, there's a lot of things that go into how people answer this question. But overall, this question is sort of measuring how much an individual in this part of the country is perceiving, the risk of climate change. So, all right, so let's move on from polls here, and let's think about climate change as a concept. What I'm going to try and do for you is give you a better understanding of how a climate scientist thinks about this problem and the tools that we use and the methodology that we use to answer a couple questions. So for one, how do scientists like myself, how do climate scientists definitively attribute climate change to human activities? How do we know for sure that climate change, global warming is because of, the burning of fossil fuels? And then secondly, how do scientists quantify the perceptibility of climate change and the idea that how do we know that if we go outside, we're able to tell that global warming is happening? How do we know that this really hot day we're experiencing was because, partly attributable to global warming? And how do we know it just wasn't, random noise or weather? So let's start with this first question. How do we definitively attribute climate change to human activities? And this goes into this relatively niche topic of climate science called detection and attribution. It's this idea that we go outside and we measure something for a long enough period of time, something that we care about, something like global mean surface temperature, for example. And we measure it for a long time, and we start to notice over time, there's an appreciable change in that quantity that we're measuring. So we detect something, a signal. And then the question is, can we attribute it to a change, or can we attribute it to a process that we think we understand? So can we attribute it to human activities? Can we attribute it to just nature, right? Is this something that nature can just produce, and we are just now observing that change because we have a long enough record? And so the example I want to provide for you here for detection and attribution is, it is that globally averaged value. It's globally averaged surface temperature. So I'm going to show you a lot of time series today, and I just want to make sure everybody understands what we're looking at here. This is, like I said, globally averaged surface temperature from 1880 to 2019. This is that data going from 1880 to 2019. Everything above zero is warmer than normal, right? And a normal is a 30-year climatology, where we take the average global temperature over 30 years and we subtract that from every value in the time series. So we're just getting an anomaly. So everything below zero is colder than that normal, and everything above is warmer than that normal. And so what you see here is this really, scary upward trend. This is global warming. This is what we call global warming, this increase. And like I said, it's about a degree Celsius over the last, 150-ish years, which amounts to about 2 degrees Fahrenheit. And so this is our signal, right? This is what we've detected as a problem, right? This is going to lead to some impacts. Now the question is, can we attribute this change that we've detected to human activities, or can we attribute it to just natural variability that the Earth would have done with or without humans? And one methodology that climate scientists use to make that determination are these global climate models, or GCMs. And I'm sure that some of you are familiar with global climate models, or a model in general, on some level. But I'm just going to spend a little bit of time talking about them. They're these massive computer simulations that represent the physical processes that lead to changes in weather and climate. So what they do is they take a representation of the Earth and they separate it into boxes, these grid boxes that are shown here. And in each of these grid boxes, you integrate a system of equations that represent the evolution of the atmosphere, the ocean, the communication between the atmosphere and the ocean, communication between the atmosphere and the land surface, the interaction between the land surface and the atmosphere and the ocean, right? The interaction between the atmosphere and the cryosphere. So we have equations to explain the evolution of all of these things, based on our understanding of the physics. And what this computer simulation is doing is it's calculating what's happening using those equations for a single time step, like a day, and then it pushes it forward. It predicts what happens the next day. Then it uses that information on that next day, and then it does it again, and it pushes it forward until you have a simulation of how things are evolving over some period of time. And it can be weeks, it can be months, it can be years, decades, centuries, millennia. These tools are really flexible, but they're also extremely powerful. And you've actually already seen a global climate model today, and that was in my title slide. This animation that I'm showing you here, which I'm hoping is smooth on your screen. It's nice and smooth on my screen, but I know that sometimes in Zoom it gets kind of laggy. But this is a climate model simulation. Now, granted, this is a very high resolution and very pretty climate model simulation, but this is simulating 1 year on Earth based on our understanding of the physics. We're watching the evolution of really just the atmosphere here, but also the biosphere. You can see different parts of the biosphere interacting with the atmosphere in this animation. And if you can see these shadows here that are crossing over the planet here, this is a day, right? You're seeing nighttime as it passes across, just to give you a sense of time here. But climate models are, they're really powerful tools. They can give us information about basically anywhere on the globe for any part of the year for a very long time if we want to integrate these models forward for hundreds or even thousands of years in some cases. Now, some models are more realistic than others. This is, as I said, a particularly high resolution model, but most models are coarser than this. Their grids they represent a larger area. This model probably has a grid of maybe 1/10 of a degree, so about 10 kilometers, probably less, to be honest with you, maybe 5 kilometers resolution in their grid. I would say a typical climate model is about a 1 degree, so about 100 kilometer representation at any given part of the Earth is sort of their standard resolution for a grid. But as I said, GCMs are really useful for answering these questions of detection and attribution, and that's because they have switches that you can flip, right? You can turn on and off different factors, and you can force the model with different parts of the climate system to see how well the climate model reproduces what we observed, given different chunks of information. And those chunks of information can include things like what we call natural factors, or different external forcings to the climate system that occur naturally. So these are the things that happen to that will influence something like global mean surface temperature that have nothing to do with humans at all. For example, solar variability, right? The sun can just emit more or less radiation to Earth, and that will cause changes in surface temperature. There can be, really subtle changes in Earth's orbit that, actually lead to really dramatic changes in surface temperature. There could be volcanic eruptions when a big volcano erupts, and it's a massive eruption. Aerosols, really shiny dust particles, will get high up in the atmosphere, and it'll reflect sunlight, and it'll actually cool the planet. So these can lead to appreciable changes in global mean surface temperatures. And so you can flip a switch, right? You can ask the question, if we just focused on the natural factors, and when we told the model, that's the only thing that can change your global mean surface temperature, can we reproduce what we saw in the real world? Can it reproduce that upward global warming trend? Well, let's do that, right? Let's just run a climate model for 150 years, and let's only force it with the changing in the natural factors that we've measured, and see how well it reproduces the observations. And so that's what we're showing here. The black is a time series of that global mean surface temperature and observations that I showed you before, right? It's that scary upward trend. And you can ignore the yellow for a second, but the blue and the red are showing you climate model simulations, a bunch of different climate model simulations where they force the model only with this natural forcing. So only changes in solar variability, orbital forcing, and volcanic eruptions. And basically what you can see is that, after about 1960, the observations in the models diverge, right? Excuse me, they diverge and they're different, and it's a pretty significant difference, right? You start to see that we can no longer explain what happened after about 1960 just with natural forcing. So this right away suggests, right, you need something else, right? None of these factors can explain what we observed, based on our understanding of these physics. So what happens if we include other things, right? Let's include things that we know that humans change in the climate system that we know lead to, based on our understanding of the physics, lead to changes in surface temperature. So for example, greenhouse gases, right? If we burn fossil fuels, right? Burning fossil fuels is taking liquid carbon and oil, and it's burning it leads to combustion, and that adds CO2 to the atmosphere. Carbon dioxide is a very potent greenhouse gas. And a greenhouse gas is very good at absorbing infrared radiation, long wave radiation that's being emitted by the planet, the Earth, us, like anything at Earth-like temperatures is emitting infrared radiation. CO2 is a very good absorber of that radiation, but because it's a good absorber, it's also a good emitter, right? So it absorbs that radiation and then emits it back down at the surface, and it keeps the planet warm, right? It insulates the planet, and that's the greenhouse effect, which is a good thing because the planet would be a lot colder than it otherwise would be without the greenhouse effect. So we need the greenhouse effect to live, right? But too much of a good thing. We know that if we increase CO2, the greenhouse effect gets stronger, right? And this is the main driver of what I'm going to show you is the main driver of global warming. But there are other things that humans interact with the climate system that can also lead to changes in surface temperature, things like ozone depletion, right? Ozone is a molecule that lives in the upper parts of the atmosphere, or the sort of the middle parts of the atmosphere, the stratosphere. And it mostly, it protects us from really harmful UV radiation, so really bad solar radiation. It's the sunblock of the planet. But because humans used a certain kind of chemical in refrigerants and aerosol cans in the 80s, these chlorofluorocarbons, or CFCs, those man-made chemicals broke down ozone in that part of the atmosphere, and we lost a lot of ozone, and we let in stronger solar radiation because of it. And that actually does also warm the planet when you let in stronger solar radiation. Also, humans cause pollution, and that pollution is full of particles, these aerosols that are shiny. They reflect sunlight. Pollution is actually a cooling impact on the planet. And then also humans' land use changes are also leading to changes in temperature. So, for example, we're cutting down dark green forest, which is not particularly shiny, and replacing it with shiny things like concrete or buildings, right? And those things can reflect sunlight more, and it actually cools the planet as well. So now let's force a model, with those natural factors, but also the human factors, right? And can we reproduce observations with the human factors in tow? And that's exactly what happens, right? When we include the human forcing, we're able to reproduce what happens, particularly after 1960. So this is already a nice piece of evidence that you need the human factors to explain what we've observed to reproduce the signal that we've detected, right? And so this is one form of attribution that we use. Right. And just reiterating that you need the human forcing. And in this case, we mostly need CO2 changes to reproduce those observations. But, a very fair question that somebody could ask here is, are CO2 changes really driven by humans? CO2 changes have happened in the past. They're going to happen in the future. But when I say the past, I mean in the past, long before humans started burning fossil fuels, right? CO2 has varied in the geologic past. And I'm sure a lot of you know more about that than I do. But a fair question is, are CO2 changes really driven by humans, particularly because there's a natural carbon cycle that CO2 exchanges between, the rocky Earth and the atmosphere. And one way that we actually know that's true is because of things like ice cores. So, so for those of you that are unfamiliar with this, what happens is that scientists go to places like Greenland or Antarctica, or glaciers and high alpine regions, and they drill into these ice shelves, these ice sheets of ice, and they get these cores, these long tubes of ice that are really excellent and pretty pristine records of paleoclimate up to about 800,000 years ago. The oldest ice core that we have is about 800,000, excuse me, about 800,000 years old. And what's really cool about these ice cores is that, if you're in Antarctica and you're getting snowed on, right, that snow is falling. Excuse me, goodness. That snow is falling. And year after year, you're going to get more and more snow piling on top of you. But as that snow falls, it catches little pockets of air. That snow is not uniform. It's not water, right? There's places for air to get trapped between the snow crystals, the ice crystals. And year after year, as the snow is compiling, more and more weight is added on, and eventually that fluffy snow will get compacted into a sheet of ice. But those air pockets will get locked in the crystalline structure of that ice sheet. And what ends up happening is that if you take an ice core and you slice the ice core, into these little like deli ham thinly sliced bits, you can see all of that air that was trapped in that ice, when that snow fell, and as over the eons, as snow continued to accumulate. And so what ends up happening is that these ice cores have these pockets of these bubbles that are direct measurements of air, up to 800,000 years ago. So we take these ice cores, we melt the ice, we capture the air, and we can measure the constituents of the gas in those bubbles to get a sense of like how much CO2 was in the air, up to 800,000 years ago. And these are extremely effective measurements, right? That ice core is it's something like 10% air by volume. So there's a lot of bubbles inside this ice. And we're not guessing, right? These are direct measurements that are really pristine. And we know that CO2 in places like Antarctica is a good representation of CO2 over the rest of the globe, because the atmosphere is really well mixed, right? Weather smooths over, it helps exchange gases throughout the planet. And so all these gases are relatively uniform throughout the planet. For example, like the amount of oxygen that I'm breathing here in Seattle is about the same amount of oxygen that you're breathing wherever you are in South Africa, for example. So that would be true of CO2 as well, unless you're standing next to a power plant or something. But here's a time series that represents the paleo reconstructed CO2 concentration from ice cores from about 800,000 years ago, almost to today. And I'm not showing you to today yet because I want to keep that a secret for now. But let's just look at the kind of variations that we've experienced in natural history, right? We do get big fluctuations. They're going from something like 200 parts per million, or maybe 175 parts per million, to 250, close to 300 parts per million. And for those of you that are unfamiliar, a part per million is about 0.01%. So these are relatively, they sound like small changes in carbon dioxide, but carbon dioxide is such an effective greenhouse gas that relatively subtle changes in carbon dioxide lead to really big changes in the strength of the greenhouse effect. So these swings are extremely important, even if they don't sound like fractionally like that much. But these fluctuations are completely natural, right? Humans were not burning fossil fuels 100,000 years ago, 600,000 years ago. So these are natural fluctuations in the carbon cycle, as CO2 is being exchanged between the rocky Earth and the atmosphere. But we need to get a better sense, or we need to focus in on, what are these changes and how long do these changes take to make, right? Back then, right, we were getting something like 100 parts per million increase in CO2, but over about a 50,000 year period, right? Where do we think we are today in carbon dioxide? We're way up here. Okay, we're sitting very solidly above 400 parts per million. Relative to the pre-industrial revolution in about 1880, we're almost 150-ish parts per million increase in carbon dioxide. CO2 concentrations have not been this high in about 2 million years. Ice cores can't go back that far. There are other measurements that we can get to get CO2 concentrations back further than 800,000 years ago, but we know that carbon dioxide concentrations have not been this high for about 2 million years. And what makes this so concerning is, not just the concentration. As I mentioned, the higher the concentration, the stronger the greenhouse effect. We know this because physics works. But it's the rate of change that's really concerning, right? This is part of the reason why we know it's not a natural factor, right? The natural cycle says about 100 parts per million increase in about 50,000 years. We've seen about 100 parts per million increase in the last 60 years, right? So this is already a red flag that something not natural is happening. Not to mention that this increase very strongly is correlated with the beginning of the Industrial Revolution in about 1880 or so. But again, a fair question. How do we know humans are responsible, right? This is all conjecture, right? We see this increase in CO2. We assume it's humans because it correlates well with the Industrial Revolution, but can we prove definitively, with chemistry or with physics that the CO2 that is being increased are coming from the burning of fossil fuels? How do we say that? All right, so for that, we need a bit of chemistry, okay? So the idea here is that we take a CO2 molecule, and a CO2 molecule, I'm sure I'm preaching to the choir here. I'm sure many of you know much more about this than I do. But a CO2 molecule is made up of carbon and two oxygen atoms. And those carbon atoms that make up that CO2 molecule can be made up of different isotopes. So for those that may be unfamiliar, an isotope is just a variation on the atom of an element that has a different number of neutrons in its nucleus. It's a lot of words, but all it means is that different atoms of the same element can literally have a different weight than a different atom of the same element. So there are two of the most relatively abundant forms of carbon atoms are what we call C13 and C12. And you don't have to remember C13 or C12. You just know that C13 is heavier because it has one more neutron than C12. So it just literally weighs more. And these are different isotopes of carbon. Okay, and so these properties of carbon dioxide are really useful because we can track the fractionation is what we call it. We can track the abundance of these different carbon isotopes in different parts of the biosphere, different parts of the atmosphere, and we can get a sense of how CO2 and how carbon is moving throughout the planet. For example, plants, the biosphere, it takes up CO2 and it breathes out oxygen. It's this beautiful relationship that we call photosynthesis. We wouldn't be alive without it. But what you have to understand about plants is that they're really lazy, right? Nature in general is lazy, and it'll almost always take the path of least resistance, right? It'll preferentially take up these lighter carbon isotopes. So it'll preferentially take up CO2 molecules that are made up of C12, these lighter carbon isotopes, because it's just easier to do it. The plants have to expend less energy to make that conversion, to take up that carbon dioxide than they would if they took up the heavier isotope. And then, animals that eat those plants, right? Those plants take the CO2 and they fix the carbon into their structure. They're carbon-based life forms. They have that carbon in their skeleton. Animals eat the plants and they preferentially take up those light carbon isotopes because they're in the plants. So, animals are also preferentially full of atoms that are light, these atoms of carbon that are light relative to, say, things like ambient air. So yeah, as I said, like the biosphere is what we call isotopically light. It's full of these light carbon isotopes. But this is relative to something like the atmosphere. The atmosphere is isotopically heavy. And we know that because the biosphere, if it's taking up all of these light atoms of carbon, it's leaving all of the heavy atoms of carbon in the atmosphere, in those CO2 molecules, right? You're just taking all the light stuff, you're leaving all the heavy stuff, and you're not replacing it with the light stuff. So the atmosphere in general is isotopically heavy relative to the biosphere. And so why is this useful, right? There's a lot of information, but why is this useful? Well, over time, things die, biota dies, the plants will die, the animals will die. And, over the eons, over thousands of years, these plants and animals, they fall down, they fall in a bog or whatever, and sediment buries them, and over time the sediment gets heavier, they start to get crushed under the pressure, and they get turned into goo, and we call that goo oil. And oil is isotopically light because oil is made up of the same carbon atoms. Excuse me. Oil is made up of those same carbon atoms that were in those plants and animals that was originally in the atmosphere when those plants took them up by CO2. So carbon is much lighter in carbon dioxide, or in carbon. Sorry, oil is much lighter with respect to carbon isotopes than the atmosphere. And so the question is, how does oil return to the atmosphere, right? Well, there's a couple pathways. The natural carbon cycle would see it return through things like volcanoes, but this is a relatively slow process. As I said, it takes 50,000 years for carbon atoms to sort of overturn in the natural carbon cycle. Or another way for this oil or this isotopically light these carbon molecules to make it back into the atmosphere is through industry, right? Humans have short-circuited the carbon cycle by digging into the planet, dipping into oil reserves, burning that oil, and releasing the carbon dioxide, or releasing those carbon atoms in the form of carbon dioxide back into the atmosphere. And so we can make a hypothesis based on this understanding, right? If the recent CO2 increase is due to burning of fossil fuels, then carbon and air should become isotopically lighter. And that's because we're taking our ambient air, which is full of these heavy carbon isotopes, and we're mixing together all of these light carbon isotopes that are coming from oil specifically. And that's exactly what we see. So this time series here in black is showing you CO2 concentration from the year 1000 up until about today. And this is again from ice cores. You can see that carbon dioxide concentrations were stable up until about the Industrial Revolution, right? And then you start to see this scary increase. And now I'm showing you up here in gold here, this yellowish gold time series is showing you the weight, quote unquote, weight of air, which is just saying what is the the average weight of a carbon dioxide molecule or a carbon atom in the air. And you can see again that was stable up until about the Industrial Revolution, and then since then, beautifully correlated with the increase in CO2, you start to see this decrease in the weight of the average carbon atom in the atmosphere. So this is quantitative, definitive evidence that the burning of fossil fuels is contributing to the increase in carbon dioxide. And we know from our understanding in the physics that an increase in carbon dioxide will warm the planet because of the greenhouse effect and the increase in the greenhouse effect. And so we call this process the Seuss effect. The Seuss effect being, taking that oil, which is isotopically light, burning it and adding it to the ambient air, which is isotopically heavy. Fun fact, this doctor, I think his name's Dr. Hans Seuss, so he is a Dr. Seuss. He was at Scripps where I got my PhD. Not while I was there, but sometime in the 50s, I think. But this is one of the biggest red herrings, or biggest, I forget the idiom, but this is one of the most definitive pieces of evidence that climate scientists use to know for sure that climate or that CO2 increases are because of the burning of fossil fuels. All right, so in the last few minutes here, I want to talk about, we've talked about how scientists definitively attribute climate change to human activities, but how do we quantify its perceptibility? How do we know when climate change has quote unquote arrived? And that's this battle of what we call climate signal to climate noise, and trying to understand, is climate change, global warming, is it perceptible above the realistic range of values that nature would produce with or without humans? And so just to define that more definitively here, climate change signal is inferred as a change in the climate system due to human activities. It's something that we know is happening because of increases in CO2, for example, things that we measure, things like global warming and its impacts, global warming's impacts on other things like changes in weather extremes. We know that as the world warms, hurricanes will become more intense because their fuel is ocean temperatures. There are robust changes in rainfall that we expect to happen in response to global warming and other forms of climate change. These outside ones are what we call trend signals. They're signals that happen iteratively, incrementally over decades. But then there are also these what we call quote unquote event signals, these individual like weather scale events that can be intensified by climate change, intensified by that trend, or changed in some way by that trend. But they're sort of stochastic and staccato type events that have the outsized impacts on society because they're just happening right now and they're really visceral. But these can be related to what we call climate noise. These are natural climate variations that are completely independent of human activities. These are things that would happen regardless of if humans were here. And a couple examples of those are things like what we call climate modes. These are it's not super important that you know what a climate mode is, but it's what it represents is sort of a redistribution of ocean currents or atmospheric circulation in such a way that it produces a pattern of a repeating pattern of ocean temperature or atmospheric circulation that the planet finds preferable. It's just a pattern of, in this case, sea surface temperature anomalies, or a pattern of atmospheric circulation anomalies that the planet produces over and over again with some set periodicity or some oscillatory behavior. And perhaps the most famous climate mode that you may have heard of is the El Nino Southern Oscillation, which is a form of, it's a climate mode, that something that the Earth would produce with or without humans. It happened before us and it'll continue to happen after us. And also probably the noisiest form of climate noise is just large scale weather patterns. Weather patterns being, it's blowing across, the United States, creating all of this weather, blowing across South Africa, creating your weather. That's mostly random stochastic noise, and that helps to, obscure a climate change signal. And it's really this separation between something like weather and climate that leads to a lot of misinformation or a breakdown in communication between, climate scientists and the general public. And so, for example, in the United States, we had a senator at one point come into our Congress, and he was carrying a snowball, and he said that global warming can't be happening because it's snowing right now. I have a snowball. But he does not understand the difference between weather, which is noise, and climate change, which is a signal. Because you can have a cold winter, but that doesn't mean global warming isn't happening. So maybe to hammer home that point, right? We can think about your day-to-day experiences, right? If you step outside and you're experiencing weather or some extreme event, right? Your day-to-day experiences are some combination of these two things, some combination of the signal and some combination of the noise. And on some days, the noise might be really big, but on some days, the noise will be really small. And that might change how you perceive the signal. And when we think about the signal, it's completely what we call deterministic. It's predictable. We understand the physics in such a way that we know what's going to happen. We know that if we increase CO2 concentrations by X amount, we should get X amount return in global mean surface temperature. Whereas climate noise is random, it's stochastic. We don't know the timing of events. We don't know when a particular weather pattern will arrive at a particular location, months in advance. We may know within a couple days or whatever, because that part is deterministic. The evolution over some time horizon in a little short period of time is deterministic, but the timing relative to other things on long time scales is completely random. It doesn't matter when these things happen. But as I said, some people in the world, they live in a part of the world where the climate signal is really big. And for them, their sense of urgency about climate change is going to be different than if you live in a part of the world where the climate noise is really big. And you might step outside and you have no idea that global warming is happening because all of the noise around you clutters it, right? It obscures your perception of climate science or of climate change. And so let me show you explicitly how we do that, right? Let's just say, for example, that we've been measuring some climate parameter, and we'll call it climate parameter X, okay? And let's say that we've measured it for 1,000 years, okay? And it doesn't matter what this climate parameter X is. It could be global mean surface temperature, it could be sea level, it could be precipitation in some place. But let's just say we have some year-to-year wiggle in that climate parameter X. Sometimes it's greater than normal, sometimes it's less than normal. But in reality, we haven't been measuring anything with high resolution measurements for 1,000 years. Our high resolution measurements that are really robust are typically about 100 years long. That's the length of the instrumental record as we know it for things like global mean surface temperature. So this is the length of our record. And you can see that our representation of what X is, like the realistic range across the different values that X can have, is really limited, right? And that's represented down here. This is just a histogram. It's just counting the number of times a given value of X is happening. And you can see that X in general, based on our limited knowledge, X in general is running from about -2 to 2, but we don't have enough information to know how frequently X happens relative to X at one value happens to relative to an X at another value. So we don't know if a value of 1 is any more frequently, is going to occur more frequently than a value of 2 because our record is too short. But let's say that we had more observations, right? If we push this forward, what I'm going to do is just add 100 years of information. As we do that, you can see how the histogram is starting to fill out here. As we get more and more observations, we get a better sense of the frequency of different values of X relative to different values of X. And you can see that a value of 1 or a value of 0.5 or a value of 0 is happening much more frequently than these extremes, values of -2 or even 3, -3 or 3. And you can start to see this beautiful distribution start to come up. And I'm sure a lot of you are familiar with what this distribution looks like or what it is. So let's zoom in on it, right? This distribution can be normalized in a nice way to represent the probability of getting any sample of X if you just plucked it out randomly, right? So let's just say that we picked a random year, 614, the year 614, that value is, say, I don't know, 1.5, right? The probability of having gotten that value of 1.5 for a year at random is something like 18% chance of that happening. We call this a probability distribution function, a PDF. And you might notice, and for those of you that have had statistics in college or high school or wherever, you'll notice that this distribution has a noticeable curve to it. We call this thing a normal distribution or a bell curve, right? And what's really interesting about climate science is that a lot of the things that we measure, things like global mean surface temperature and sea level and other things, a lot of this stuff is normally distributed in a nice way. And because of that, we can relate, the frequency of different values of these things happening in nature to this normal distribution. And then we can compare signals to it to get an idea of if those signals are statistically, it's just statistically different than the realistic range that nature can provide. Just for, a refresher for people that may have forgotten, a normal distribution is, I got to mention also that normal distributions happen outside of climate science, right? They occur in, all in a variety of different fields. It's just a function of large sample sizes across a population. But what's nice about a normal distribution is that the ranges of X are well known from a probability standpoint. For example, we know that 68% of the time, the value of X in our climate, quote unquote, climate parameter will fall between what we call one plus or minus one standard deviation. And the standard deviation is just a fancy way to say an average wiggle, right? If we have all of these wiggles, on average, there's going to be some distance away from zero that X is, and that's one standard wiggle. 68% of the time, X should be between plus or minus one standard wiggle. 95% of the time, X is between 2 times one standard wiggle, so twice the standard wiggle. And then 99% of the time, it's between 3 standard wiggles. And so this is really useful information because it represents the realistic range of X due to noise, right? And X again could be like global mean surface temperature. And we can quantify this realistic range of global mean surface temperature using things like climate models and paleoclimate records and all of these things to get a distribution of what nature could produce. And then we can compare our signal to that distribution and get a sense for how strong the warming we've seen over the last 150 years is relative to that distribution. So for example, if our signal were to fall within the distribution, right, then we can't really say that, we can't say the thing that we've detected is any different than what nature could produce if the signal was, if it falls reasonably within the distribution. However, if our signal is way outside the distribution, it's a value that nature has never produced, then we can say with statistical certainty that our signal is statistically different than the noise, and it's not something that nature could have ever produced. And so how big is big enough? How big does the signal have to be relative to the noise to say that a climate signal is different than the noise? Well, our typical value is 2. So if you take the ratio of the signal relative to the noise and it's greater than 2, you can say with 95% confidence that your climate signal is significantly different from this realistic range of climate noise. And so what I'm going to do now is just show you what that looks like in space. Let me jump here. So let's take a climate model. Okay, and what I'm going to show you is the surface temperature signal. So what by that I mean is we just take the trend in surface temperature, so the change in surface temperature from 1950 until about today. So this is how much warming we've experienced over the last 60-ish years. And I'm sorry, this is in degrees Fahrenheit. Just divide everything roughly by 2 and you'll get degrees Celsius if you're unfamiliar with Fahrenheit. And what you can see, as I said, is that signal is bigger in some places than in others, right? Over land, the signal is typically bigger than it is over the ocean. And there are chunks of land that are experiencing more signal than others. Well, what about the noise, right? We need to be able to quantify the realistic range of values that nature could produce for something like surface temperature. So we can take a model. In this case, we're going to use what's called a pre-industrial control model. This is a model that is representing a planet that has no humans on it. So it uses pre-industrial values of carbon dioxide, of solar variability, other atmospheric constituents that have been altered by human sense. And it just runs it for a very long time. So as I mentioned, our observational record is too short to really quantify the relative range of climate variations. So we have to simulate the planet for in this case, 1,000 years, so several hundreds of years, right, to get a better representation of that distribution, to get that normal distribution. So what this is showing you is the value of one standard wiggle of surface temperature from this 1,000-year pre-industrial control simulation. And again, this is that representation of the noise. And you can see that noise also varies as a function of space. There are some places where the noise is much bigger than in other places, and that's marked by the darker blue. The darker blue says that the noise is much stronger. And you'll notice generally that the noise is stronger at mid-latitudes, which is sort of up here and down here, right? But now the question is, how, in what place is the signal significantly different than the realistic range of noise? And that's what's going to be shown here. This is the signal, what we call the signal to noise ratio, which is really just this map divided this by this map. And the question is, where is the signal greater than 2? The signal to noise ratio greater than 2. That's where we can say with 95% certainty that the signal is detectable above the noise. So basically inside of this red line is saying that, about today, in the year 2021, you should be able to step outside on any given day and say, well, for any given year, because this is all annual mean, but for any given year, you should be able to know that climate change is happening, that global warming is happening. You should be able to detect it because the signal is much bigger than the noise you're experiencing at any given one of these parts of any given location within the red line. But you'll notice that there's a large chunks of the planet where the signal is not quite above the noise level yet. And now that is not to say that the signal is not happening. That's not saying that global warming isn't happening for places like Russia or the northern parts of the United States or Canada. Global warming is happening for them. Climate change is happening for them. They just have a lot of noise. So because of that noise, it's obscured and it's just harder to detect. But we know it's happening because of our understanding of the large scale physics. But largely within the tropics, right? A lot of Africa, for example, is very solidly feeling, they feel the effects of climate change now. And that because of that, the sense of urgency for the problem is different for people who feel the effects of climate change now, as opposed to in the future when the signal is continuing to increase, but the noise level is just staying. So, in 50 years, the red line will encompass the entire planet. But today, this is roughly where the red line is based on this particular model simulation. But as I said, this changes the conversation for how people deal with the environmental impacts of climate change and their overall environmental or their overall political will to make a meaningful environmental policy to deal with climate change. I've been to a number of these environmental conferences that are focused on dealing with climate change that are put on by the United Nations. And, sometimes the loudest voices at these conferences aren't the people who have the most money. It's not always the United States. It's not always China or India or Europe, all these big world emitters of carbon dioxide. The loudest voices at these conferences are very often these smaller, relatively poorer nations that are feeling the effects of climate change now. And one subset of peoples that I want to point out here are this alliance of small island states. This is a group of small island nations in the West Pacific, places like Fiji and the Seychelles, who fit very solidly within this red line, right? They live in a part of the world where the climate change signal is much stronger than the climate change noise. So for them, climate change is not some far-flung problem. It's something that they're dealing with today. And they're dealing with the impacts of things like sea level rise today. They have to lease land in the mainland for their people to be displaced to, because their island nations are literally being swallowed by rising sea levels. And it's hard for someone maybe in the middle of the United States to empathize with that, because they don't feel the effects of climate change as strongly as someone who lives in a part of the world where the noise is a lot smaller. So with that, I'm just going to jump to my final slide here because I see that we're already at the hour. But I'm happy to take any questions. I'm happy to stick around. I really appreciate your attention. Here's my email. Please feel free to email me if you have any questions or if you want to discuss more offline. But with that, I'm going to pass it back. And yeah, happy to discuss. Thank you.
Dillon, thank you very much for this. There were some interesting graphs, and it was very well presented and very well illustrated. We'll take questions from anybody who would like to have any. I'd like to make one comment or one question to start off with. You haven't said too much about or anything about methane. Should we be as worried about methane as we are about CO2?
Yeah, that's a really great question. So methane, for what it's worth, you can measure the greenhouse effect of a given molecule of a gas, and you can basically say like how much infrared radiation would it absorb for a given increase in carbon dioxide, or given an increase in that the constituents of that greenhouse gas. So I didn't say that very eloquently, but the idea here is that methane is 1,000 times more efficient of a greenhouse gas than CO2, but it's also something like I don't know the percentages, but it's not infinitely. It's like 100 times less abundant than CO2 in the atmosphere. You measure methane in changes in parts per billion, and you measure changes in carbon dioxide in parts per million. So methane is like 0.0001% of the atmosphere right now. Not to say that changes in methane aren't important, because it is, like I said, 1,000 times more efficient of a greenhouse gas than CO2. but the concentrations we're dealing with are much, much smaller relative to carbon dioxide. Also, we know we have a better handle on the problem for carbon dioxide. We know where a lot of the carbon dioxide emissions are coming from. Not to say we don't know where methane emissions are coming from, but the solutions are less clear for how we deal with methane. A lot of methane emissions come from agriculture and also from melting permafrost, right, and in high latitudes. So methane is definitely a priority, but CO2 is sort of number one, just given its concentrations. It's way more abundant.
Are there any more questions or comments?
I see a couple in the chat. Well, I see some thank yous, but
Can we hear
Alan, do you have? Go ahead.
Yes, Dillon. You've shown us many graphs based on the history with a terrible change happening now. So what are your predictions for the future? Have we left it too late? Can we change anything? What about the future? What's happening?
Yeah, that's a good question. So we actually just released, we being the climate science community, just released the newest, latest and greatest set of climate models that have been updated based on our improved understanding of the physics. And they predict by the year 2100, we're expecting, worst case scenario, sort of a business as usual scenario where we don't make any changes to the way that we live our lives. Something on the order of between 3 to 4 degrees Celsius change in global mean surface temperature. And some models predict even more, something like 5 or even 6 degrees change in global average surface temperature. And you got to remember, these are globally average numbers. So there are some places that are warming much more than that. Like the high latitude Arctic is projected to warm by anywhere from 10 to 15 degrees Celsius, which is a crazy number. I cannot fathom that world where, the Arctic is warmed by something like 10 to 15 degrees Celsius in less than 80 years from now. I will say there is uncertainty in that number. And that's why I give you quite a range, right? Between 3 and 6 degrees Celsius, because we don't, there are some outstanding questions in the way that we represent things like clouds and climate models. But we know that, the biggest warming is still ahead of us. There's still time to sort of, mitigate. And that, again, as I said, that's the worst case scenario. There are scenarios where we do drop our emissions by some level. And, we're already going to experience some fraction of global warming. Every year that we continue to emit CO2, we're committing ourselves to, a certain level of global warming. And that's because CO2 has such a long residence time in the atmosphere. It lives in the atmosphere for 50 to 1,000 years, depending on where you are. So every year that we're emitting CO2, we're committing ourselves to some level of global warming. We're already at a degree. I see someone in the comment asking if we're going to stay below this or reach this 1.5 degree goal. I do not think we're even going to get close to the 1.5 degree goal. Something to realize about something like the Paris climate agreements is they're a little deceptive. They say that we want to stay below 1.5 degrees or stay below 2 degrees. But what they mean by that is the equilibrium temperature. They don't mean they want us to equilibrate. When things stop changing, they want us to stop changing at about 1.5 degrees or 2 degrees C above previous or pre-industrial values. They don't say this, but they don't know, or they don't care how much we overshoot that initially. We're going to cross 1.5 degrees. We're going to cross 2 degrees. We're already committed to it by the amount of CO2 that we've emitted. The question is, can we bend the curve? Can we turn it back down and come back down to a level that is acceptable? The real issue here is how much we overshoot those acceptable levels. And, climate models are projecting something like 4 degrees Celsius by 2100. And that's a problem.
That is a serious problem. I think it's something we can all think about. Are there any other questions or comments for Dillon?
Sorry, Dillon, me again. The higher temperatures, will that mainly affect climate? Is that the main thing, that the high temperatures will, the global climate?
Well, so global climate, the higher temperatures will affect, so there's a couple things. Higher temperatures will affect the availability of, it'll affect the amount of like land ice. So global warming, melting sea ice doesn't matter because that sea ice is already displacing water. But if you melt land ice and you add water to the oceans, you cause sea level rise, right? And I mentioned those islands in the West Pacific that are already experiencing catastrophic sea level rise. That begins to become a real issue for more industrial nations, in the next 100 to 200 years as more and more land ice begins to melt. For example, we're very, very worried about, a section of Antarctica that is particularly sensitive to changes in temperature. And if that goes, there are sort of thresholds of land ice melting that are irreversible. So if we melt a certain fraction of land ice of that ice sheet, it'll go and we can't stop it no matter how much CO2 we take out of the atmosphere. If these particular ice sheets go, I mean, the sea level equivalent of some of these ice sheets are tens of meters of sea level change, which again, that's a globally averaged value. In some places that can be much higher. So I would say that's the most immediate society altering concern in the next 100 to 200 years is sea level rise. That's going to displace, billions of people around the world who are living in low-lying coastal regions because that land will not be there anymore. Maybe the most immediate impact is climate change impact on extreme weather. So things like drought and wildfire. There's good climate science, good papers that I can forward to people about the impact of, global warming is pushing the distribution of temperatures towards warmer values. So the frequency of extreme warmth is going to be more and more frequent as a result. And there are places that are equipped to deal with really hot weather, but there are places that are not equipped to deal with really hot weather. And that will be a problem in the near future as well. Yeah, don't buy at the coast. I'm seeing in the chat here.
For those of us living at the coast, this is of some concern. Dillon, I think I'll cut the question and answer session there. I'd like to thank you very much for presenting to us tonight. The talk has been recorded and it will be on the GSSA YouTube channel within a couple of days. We'll probably advertise it a little bit, but it was an excellent presentation. Thank you very much. Nolene, do you have anything to add?
No, thanks. That was fascinating. Thank you so much, Dillon, for giving up your time. And go enjoy your breakfast now.
Thank you. I appreciate the opportunity.
Thank you all for attending. I will close the meeting now. Thanks a lot, Dillon.
Thanks. Take care.